Okay, water is super awesome. We've all agreed on that. It's super important. Water has a bunch of very unique properties that make it unique. Yes, unique properties that make it unique. And they're largely all because of the extensive network of hydrogen bonding. So whenever we're talking about solid water or ice, it has the most hydrogen bonds. Whenever we're talking about water in its liquid form, the number of hydrogen bonds has been disrupted because these molecules are moving all around. And then whenever we vaporize water, well, we're going to have the least amount of hydrogen bonds between water molecules because the distance between them. So water has a very high melting and a very high boiling point. Water also has a very high heat capacity. Now, if you remember, specific heat capacity is the amount of energy that is required to change the temperature of 1 gram of a substance 1 degree Celsius. So water will store and absorb heat and release it very slowly. So thermal properties, well, water has a very high heat of vaporization. The energy required to vaporize 1 mole of liquid at pressure of 1 atmosphere is your heat of vaporization. High heat capacity and high vaporization help maintain living systems temperature. So warming and cooling, warmth is absorption and cooling is evaporation. Basically, water is acting like a really good thermostat for your body due to its innate characteristics. So when you're when you're sweating, that's actually cooling you down, whereas that's cooling you down because it's evaporating off your body. And whenever you're warming up, then it's absorbing. Your body is warming. Your body is absorbing water. Okay, solvent properties of water. Hydrophilic molecules. Well, hydrophilic molecules are going to dissolve within water. Water dissolves both ionic and polar substances by forming what are known as solvation spheres. So here what we have is NaCl, solid, which has dissolved. It's dissociated into a sodium ion and a chloride ion. And we've got this solvation sphere of all these water molecules that are surrounding them. So hydrated ions have reduced attractive forces between them. So that's actually what we're observing there. Hydrophobic molecules are insoluble in water. And what we observe here is the hydrophobic effect. And this is driving force in hydrogen bonding of water. Now, amphipathic molecules contain both polar and nonpolar groups. We already talked about these in the context of lipids. We have a polar head and an aliphatic or a nonpolar tail. This is what forms micelles, where we have this network of water molecules that are all hydrogen bound to one another surrounding those micelles. Osmosis is important for cells. Isotonic solutions have the same solute concentration, so you have no net movement of H2O. The cells stay the same size. Hypotonic solutions have a lower solute concentration, so water moves into those cells. These cells are going to swell and rupture, not wupture. Hypertonic solutions have a high solute concentration. Water moves out of those cells, and those cells are going to shrink and shrivel up. Now, here's our spectrum. We've got a hypotonic solution and a hypertonic solution. In a hypotonic solution, we have more solute inside the cell than in the solution surrounding it. Water is going to move into those cells. Now, in a hypertonic solution, you have less solute inside the cell than in the solution around it, and so water is going to move out. Water ionizes. So liquid water can ionize into a hydrogen ion and a hydroxide ion. These hydrogen ions do not exist in an aqueous solution, but instead you have hydronium ions. So we have an equilibrium constant where we look at our products over our reactants, and our products are H3O concentration times OH minus divided by our concentration. No, rats. Concentration of H2O. So what I was trying to display there was KEQ, H3O plus, OH minus, divided by H2O concentration. Okay, close. Hydrogen ion is one of the most important ions in a biological system. Hydrogen ions affect most cellular and organismal processes. The pH scale is a measure of the hydrogen ion concentration. Now, an introduction to logarithm, because because this is, you've seen this in Gen Chem 2, but we're going to revisit it. In its simplest form, a logarithm answers the question. How many of one number do we need to multiply to get another number? For example, how many 2's do we multiply to get 8? Well, 2 times 2 times 2, we need 3 of them to get to 8. We need 3 2's to get to 8. Okay? So the logarithm is 3. Now, in a base 10 number, a logarithm can be written without a base like this. Log 100. The implication here is that this is log 10 100. This is the common logarithm. Scientists love to use it. On a calculator, it's indicated by log. So that right there is equal to log 10 of whatever number that you plug in there. So essentially what this is how many times do you need, or how many times do you need to multiply 10 to get to a particular number? So an example would be log of 1000. The implication is it's 10 there. So how many times do you need to multiply 10 by 10 by 10, or sorry, how many times do you need to multiply 10 by itself to get to 1000? So log 10 of 1000, or log base 10 of 1000 is 3. Now, our pH scale uses that log scale. So pH is equal to the negative log of the concentration of our hydronium ion. And this is analogous to negative log of hydrogen ion concentration. pH scale measures acidity without using exponential numbers. So we have a range from 0 all the way up to 14. The added acids increase hydronium ion concentration, and bases increase the hydroxide ion concentration. This range is from 0 to 14, with 7 being in the middle, that being neutral. Now, our hydrogen ion concentration for a neutral pH would be 1 times 10 to the negative 7th. And anything lower than that is going to be acidic. Anything higher than that is going to be basic. Now, some common fluids that you'll see from time to time. Well, you have extremes that maybe aren't common fluids that you see from time to time, but our extremes are concentrated sodium hydroxide and concentrated HCl. These are strong bases and acids respectively. Blood has a pH of about 7.4. Seawater has a pH of about 8, which if you ever go to the Gulf or something like that, you can pick up, you touch the water and it's got this slipperiness to it, and that's because it's a little bit more basic. So yeah, there's your examples of solutions. Now, the importance of hydrogen ion concentration, this is one of the parts of the water chapter that I really, really enjoy. Because hydrogen ion concentration influences the substance, or influences the appearance or the state of a molecule in a solution. So if we look at these two amino acids, again, we're getting into amino acids later, but if you look at this amino acid right here and this amino acid right here, an acidic amino acid is going to act as a hydrogen ion donor, and a base is going to act as a hydrogen ion acceptor. Now, this group down here, and this group here and here, well, based on the hydrogen ion concentration, this group is either going to be protonated or it's going to be, deprotonated. And the implications of that are this group is either going to be positively charged, or it can be negatively charged, or it can be neutral. So based on the hydrogen ion concentration, you're going to see a variation within that. Now, acids and bases, strong acids and bases completely dissociate. We learned that in Gen Chem 1. We had a set of, I think it was 7 strong acids, sulfuric acid, HCl, oh boy, oh rats, yeah, sulfuric acid, hydrochloric acid, nitric acid, hydrobromic acid, hydroiodic acid, nitric, perchloric. Yeah, perchloric, hydrochloric, hydrobromic, hydroiodic, nitric, and sulfuric acid. Those 6 are your strong acids. You have quite a few more strong bases. Your group 1 metals with a hydroxide ion, those are going to be good examples of strong bases. And then you've got a couple of others with like calcium hydroxide, for instance, is a strong base. So anyway, when it comes to acids, most of them are weak acids. And so they do not completely dissociate. So if you had something like what is displayed right here, well, a strong acid, you have HCl totally breaking down to H plus and Cl minus. Now, this right here is a little bit correct, but it's a little bit off, because you've got this ionization, HA breaking down. Well, the hydrogen goes with the H3O plus, the A remains alone, but you've also actually got the HA there because you don't have complete dissociation. So the strength of an acid is also measured by its Ka or its pKa. A larger Ka is going to indicate a stronger acid. A smaller pKa, therefore, is also going to indicate a stronger acid. Now, what's the difference between pH and pKa? Well, we're going to look at this in the context of something known as the Henderson-Hasselbalch equation. pH is equal to negative log of the hydrogen ion concentration. Ka, an association constant, is equal to the hydronium ion concentration times A divided by HA. pKa equals negative log of Ka. Okay, so basically whatever this value is, plug that in, negative log of that, and you get pKa. pH is the reciprocal of the logarithm of the hydrogen ion concentration. That seems a little bit wishy-washy and confusing, but I assure you, as long as you have a calculator, you're going to be good. We're largely going to speak in the language of pKa's, so just keep that in mind. pH gives an idea of the amount of hydrogen ions present in the medium, or in the solution. pKa gives an idea of how much of which side of the equilibrium is going to be favored. So the degree of acid association or dissociation. So when you think about something as what's going to be favored, if you think about this molecule right here, HA that will dissociate into H plus H minus, is there going to be more of this or more of this? And we base that on our pH. So the Henderson-Hasselbalch equation, which is displayed behind my head, but I'm going to go ahead and rewrite it, that is equal to pH, or sorry, the Henderson-Hasselbalch equation is pH is equal to pKa plus log of the dissociated times the associated. I always like to look at this as the deprotonated. I'm just going to write DEP, D-E-P, deprotonated, versus the protonated form. Now, buffers. These are an important part of basically life in any sort of scientific experiment. Buffers are very effective and successful at regulating pH of a solution. A buffer is a solution that can resist large pH changes upon addition of a stronger acid or a base. They're going to help maintain hydrogen ion concentration. Blood and cells are buffered, and blood pH ranges from 7.35 to 7.45. If the pH is below 7.35, you're dealing with not a phenomenon, but you're dealing with an affliction known as acidosis. If the pH is above, blood pH is above 7.45, that's alkalosis. So either it's a basic environment, too acidic, or a too basic environment. Now, most buffers are weak acids and their conjugate bases. A weak acid or base can buffer plus or minus 1 pH unit from the pKa. So if you learn something about a molecule that has a pKa of 2.65, well, that weak acid is effectively a good buffer within the pH of 3.65 all the way down to 1.65. Now, once the pH is below that, if you add a little bit of acid, the pH is going to plummet. It's that molecule or that substance is not really effective at saving or maintaining a pH. So can it kind of take a hit of a strong base, or can it not? Within that buffering range, yes, it can, but outside of that buffering range, the molecule doesn't work anymore. Buffering capacity is the ability of a solution to maintain pH. This is dependent on the concentration of the protonated form of an acid and deprotonated form of an acid. The ratio, specifically, of that protonated form to the deprotonated form. The more molecules of buffer present, the more hydrogen ions and hydroxide ions that can be absorbed without altering the pH. You need to develop a mathematical description of the relationship between pKa and pH. Now we're going to be looking at this, visualizing this quite often, especially when we talk about amino acids. So that's the way that you're going to see this most often. So this is an example of a titration curve. I know that you guys have probably all done titration curves, but one of the things that I want to draw your attention to is the label for the axes. The y-axis is your pH, the x-axis is your sodium hydroxide equivalence. So this point right here is where you have a 50% of the molecule looks like this. Right here, and 50% of the molecule looks like this. And I'm going to go ahead and draw a line, or circle it. So this molecule that's displayed right here is acetic acid, and this molecule right here is acetate. So at that exact pH, we have an equal concentration of the deprotonated form and of the protonated form. So when our pH equals our pKa, that's what we've got, an equal concentration of the deprotonated and the protonated form. Now what that means is if our pH goes lower, if our pH drops below this range, or actually if our pH is below our pKa, then what we have is a higher concentration of this form, because that's our protonated form. If our pH is above our pKa, pH greater than pKa, then this is the form where the deprotonated form, our more basic, our deprotonated form is more present, or in higher concentration. Okay, there's our range. Now, how can we predict the pH of a buffer? The pH of a buffer is determined by two factors. Ka, different weak acids are going to have different equilibrium constants and different Kas. The ratio of our deprotonated to our protonated form in a buffer also affects the pH. If a buffer has more base than acid, more hydroxide ions are likely to be present and the pH will rise. When the deprotonated form is equal to our protonated form, the hydrogen ion concentration is equal to our Ka. So our pH is equal to our pKa. The Henderson-Hasselbalch equation, which we've already kind of looked at, is derived from the equilibrium expression for a weak acid. This enables us to calculate the pH during a titration and to make predictions. So derivation of our Henderson-Hasselbalch equation is when our deprotonated form is equal to our protonated form, our pH is equal to our pKa. When our, this is basically the information that you need to take away from all of this. When our deprotonated form concentration is equal to our protonated form of the molecule, then our pH is equal to our pKa. When our deprotonated form concentration is higher than our protonated form concentration, then our pH is greater than our pKa. When our deprotonated form concentration is lower than our protonated form's concentration, then our pH is less than our pKa. So an example for this, calculate the pH of a mixture of 0.25 molar acetic acid and 0.1 molar acetate. So our pKa is equal to 4.76. Okay, so what we need to do is look at our Henderson-Hasselbalch equation. pH equals pKa plus log of our deprotonated form, this guy right here, which I'm just going to write 0.1 divided by our protonated form. 0.25. So I'm going to use my calculator, and I will say 0.1 divided by 0.25, and what is the log of that? That's going to be negative 0.3979. So negative 0.3979. Okay, so my pKa is 4.76. So my pH is effectively 4.76 minus 0.3979. Now, you might look at that and say, does that make sense? And I want you to look at that and say, does that make sense? 4.76 minus 0.3979. That means our pH is equal to 4.361. Or 362. Does that make sense? Okay, well, let's think about this. We've got a protonated form and a deprotonated form. We know our pKa. Our pKa is unique for our molecule. We have a higher concentration of the protonated form. And that is greater than our deprotonated form. So what does that mean? That means we have a higher concentration of hydrogen ions, or it's a high enough concentration that, well, all of our molecules are grabbing onto those hydrogen ions. So this does make sense from that lens, or through that lens. And there we go. Yeah, I already did that. Yeah. There we go. That's what I said. 4.36. Okay. Now there are a number of important physiological buffers. The bicarbonate buffer system, also known as the blood buffer system, we got 2 pKa values. Only one ionization is physiologically relevant. So CO2 plus H2O yields H2CO. 3. At a pKa, or pKa 6.37, that's when we see this dissociation of this hydrogen ion and HCO3 minus. So at a pH of above 6.37, well, this is what we're going to see. The phosphate buffer system is also important from a physiological standpoint. This is also known as the intracellular fluid buffer. It's got phosphoric acid has a total of 3 pKa values. Only one of those ionizations is physiologically relevant, and that's the one at 7.2. At pH below 7.2, this is the molecule that's going to be most common. At above 7.2, this is the molecule that's going to be most common. So we have this interchange, or this interplay between those two. Now, a protein buffered system contains several types of ionizable groups and side chains. They're going to donate or accept protons. An example, hemoglobin. Hemoglobin can bind small amounts of acid in the blood, helping to remove that acid before it changes the blood's pH. Many other proteins act as buffers as well, because they're able to bind those hydrogen ions and disperse them when needed. Proteins containing the amino acid histidine are particularly adept at doing that. And the reason for that is histidine has a pKa of approximately 6.1. All right, so that wraps up our water chapter. I gotta let you know that this is all going to be very, very important. We're going to revisit this when we talk about amino acid structures. But if this is something that you're struggling with, please reach out to me, and I'd be glad to help you out with some of these things. So, yeah, make sure that you feel good about titration curves and you understand the concept of if the pH is lower than the pKa, what are the implications? If the pH is higher than the pKa, what are the implications? All right, well, have a good one.